chapter 4.5 or 4-5, factoring polynomials. If we look at the objective, is to factor polynomials by using the GCF by recognizing special products and by grouping terms. So there's a couple things that we're going to deal with here. So the first thing, factoring a polynomial. So if we look at the example number 1, we have 3 terms here. We have 3x to the 4th, we have negative 6x to the 3rd, and we have positive 12x. So if we were going to factor the GCF, we're going to look at those 3 terms, and we have, let's do it in this fashion, 3x to the 4th, we have negative 6x to the 3rd, and we have 12x squared. So let's do the prime factorization, which is negative 1 times 2 times 3 times x times x times x, which equals 2 times 2 times 3 times x. We wanted to find the greatest common factor. We're going to circle the common, so they each have a 3 in common, they have an x in common, they have a second x in common. So the GCF is going to be 3 times x, or 3x squared. So we're going to take that out. Now, using our factor pairs, if we have this term, and this is how it's written, so we do 3x to the 4th minus 6x to the 3rd plus 12x squared. So we are going to pull out a common factor of 3x squared. Here's the cool thing about our factor or our prime factorization. Whatever is left, aka the leftovers, is going to be what we are going to be left with after we factor it out. So there is an x squared. So we would write x squared. That's if we factor 3x squared from 3x to the 4th, we're left with x squared. That's the cool thing about this prime factorization writing this way. So if we want to know what's left, that's negative 1 times 2 times x, or negative 2x. So negative 2x. If we factor a 3x squared from negative 6x cubed, we're left with negative 2x. And if we are, somebody's waiting for me, if we factor out the 3x squared from 12x squared, we're left with 2 times 2, or 4. So that is plus 4, and that's a nice way. So that is considered factored, the GCF out. Now, factoring this trinomial inside is another section, but not this section. So that's the first thing, is factoring out the GCF from each of these. And we see that the GCF of the terms is 3x squared. And so if we take a 3x squared, we're left with that, which is. So that's what's happening. And we can use that prime factorization to see what's left in that quantity. It's a really, really neat thing. Now, these special factor patterns are definitely whole nother subject. And this is more of an algorithm. I talked about algorithms when we were multiplying conjugates, when we were multiplying binomial squares, whether they had a negative in the middle or a positive in the middle. We knew that we could apply an algorithm to produce our product, the product of those two. So there were shortcuts to help us when we saw that in multiplying. We would also use those same algorithms to recognize the patterns to go backwards. So that factoring, that reverse. So factor each polynomial, and you should be getting so good that you don't have to write the prime factorization, and our GCF is going to be what they have in common. So they have a y in common, so my GCF is y. So I'm going to factor out that y. That's my GCF, goes on the outside, and then what's left over? So I have a y left over, so I need to write a y in there, And what's left over in the second term? Well, if I take a y from y, I'm not left with 0, I'm left with 1. So this is the factoring of that. Outside is always going to be the GCF, and inside the parentheses is going to be what's left over. So we have 4x minus 28, 4x negative 28, prime factorization, negative 1 times 2 is 14 times 2 in there. What is my GCF? I have two 2's, so my GCF is going to be a 4, not a 2. I can factor out a 4. What am I left with? I'm left with x minus 7. That is how we factor polynomials. Pretty cool, right? Pretty neat. Now, some of you are going to get so good that you can eyeball it, but we will continue doing the steps using prime factorization. 2 times 2 times 2 times a times a times a times a. Negative 1 times 2 times 7 times a times b. Let's just circle what they have in common. They have a 2 in common. They have an a in common. They have a second a in common. So my GCF is going to be 2a squared. When I factor that, what am I left with in the first term? That's 4a squared. What am I left with in the second term? Negative 7b minus 7b. Really, really nice technique. Hopefully you see it. Negative 8x cubed minus 10x to the fourth. First thing we should recognize, step 1 is make sure it's in standard form. So this should actually be negative 10x to the fourth minus 8x to the third plus 6x squared. And here is a tricky little thing that they're going to do to you already on the fourth problem. So we have a negative 1 times 2 times 5 times x times x times x times x. We have negative 1 times 2 times 2 times 2 times x times x times x. Look, my first term is negative. There's an understanding that when your first term is negative, you have to factor out a negative. And that's easy in the first two problems because we see the negative. But this one doesn't have a negative. So if I did the prime factorization of 6x squared, it would be 2 times 3 times x times x. But I just told you that I need to pull a negative. Well, there aren't any negatives. Well, how can we creatively create a negative? Do you see what I did there? If I introduce two negatives, that still makes this term positive 6x. And it allows me now to pull out a GCF of a negative 1. So we must pull out a negative. We can pull out a 2. There's only 1, 2. We can pull out an x. We can pull out a second x. So my GCF is going to be negative 2x squared. I have to factor out a negative if it's there. What are we left with from negative 10x to the fourth? We're left with 5x squared. We're left with 4x. And we're left with negative 3. Oh, baby, look at that. So that would be the proper way to factor that polynomial. 10x to the 8th, 15x to the 7th, negative 35x to the 5th. Since my first term is positive, I don't have to factor out a negative. I just have to factor out a positive, whatever the GCF is. 2 times 5 times 2, 3, 4, 5, 6, 7, 8. 3 times 5, 1, 2, 3, 4, 5, 6, 7. Negative 1 times 5 times 7. 1, 2, 3, 4, 5. So what do they have in common? I'm going to do this shortcut. We see this. And then I should know that I have 5 that I can pull from here. So that means the maximum I can pull from here is 5. And I can pull 5 from here. can't pull more than my smallest number. Hopefully some of you have already seen the logic behind that. So my GCF is going to be 5x to the 5th. Greatest you take the least, least you take the most, the greatest. That's a little trick I taught my students back in the day. So you're left with 2x to the 3rd plus 3x squared minus 7. That's how you factor. And we can look now, let's look at the coefficients. So here's the other way that we can move towards. When you get good, you look at the coefficients, and what is the largest? You should be able to see, oh, I can factor out 11. It's my largest GCF. Now we can look at the variables. Let's look at all the a's. You have a to the 3rd, a to the 2nd, a. Remember, GCF, greatest you take the least. What's the smallest a variable? I can take a to the 1st. Now let's look at the b's. I have b to the 1st, b to the 2nd, b to the 3rd. I can't take more than the least. So my smallest is b to the 1st, so I can only pull out. That's my greatest common factor. So if I take 11ab, I'm left with a squared. If I take 11 from negative 22, that's negative 2. A from a squared is a, b from b squared is b. 11 goes into 55, 5 times a. I only had an a, so I have no a's in this. B, I take 1 from, and I have b squared. So that's the other way that we can do this. That's good, it was the last problem. All right, now we have the special cases. So in example 2, what are the characteristics? Some of the characteristics that I will show you in the perfect square trinomials, that's A and B, is notice that every perfect square trinomial or binomial square, because it creates a binomial squared, has a second term positive. And then the other characteristic is the first and last are perfect squares. And now, here's the cool thing is, this sign will always go, and this sign will always go into your binomial square. Okay, that's always going to be the indicator. And what we are doing is, this is the hard part, your middle equals the square root of the first times the square root of the last doubled. What do you mean by that? Well, let's do that. Square root of the first is z, square root of the last is 4, and then double it. That makes 8z. That makes 8z, yeah. And so that equals my middle. So yeah, that equals. If that equals your middle, then we would just take the factor of the first and the factor of the last. So we see the 4 and the z located here. So square root of our first, 3, that's a horrible 3. Square root of our first is 3x, square root of our last is y. If we multiply it and double it, does it equal my middle? Yes. And now notice that I take these first and last, and that's what that produced. Now, for C, the other example is the difference of squares. So it literally is the difference, subtraction of two perfect squares. So in order, if that hits it, it's two terms, subtraction, both the first and the last are perfect squares. When we take the perfect square of, when we take the square of 36m squared, that's 6m. Take the square root of 49n, that's 7n. You'll notice that, and we have to create conjugates. Why do we have to create conjugates? Because there's no middle term. Okay, and then 3, we have to GCF first and then look and see for special cases. So it's 3 terms. That's the first thing we should, 3 terms. That's, is it a binomial square? Binomial square is our question. We should go through this. Is it 3 terms? Is the second sign positive? Meaning this. Is the second sign positive? Yes. And when we say 3 terms, we're talking 1, 2, 3. 3 terms. So yes, 3 terms. Yes, second sign is positive. The next thing we should look is, are the first and third terms perfect squares? Are they perfect squares? Are the first and third? Is this and this a perfect square? Yes. X squared is a perfect square. 25 is a perfect square. And now, here's the hardest part. Does the middle term, 10x, equal 2 times the square root of the first times the square root of the last? So 2 times the square root of the first is x squared. Square root of the last is 25. So 2 times x times 5, does 10x equal 10x? Yes, it does. Yep. So that tells me it's a binomial square. So I know that it's going to be a binomial square. This sign will go in here. That's going to be that sign. And then we take the square root of the first. So we get x. And we take the square root of the last, which is 5. And that's my answer. X plus 5 quantity squared. So 3 terms. 3 terms. Yes, we got 3 terms. Second sign positive. Yep. Our first and third perfect squares. Yep. Now, does the middle equal 2 times the square root of the first times the square root of the last? Does 16a equal 2 times the square root of a squared times the square root of 64? 2 times a times 8, 16a. Yes. So I'm going to write a binomial square. This sign is my sign. I'm going to take the square root of a squared, which is a. I'm going to take the square root of 64, which is 8. And there it is. 3 terms, yes. Second sign positive, yes. 2 times first and third terms perfect squares, yes. 2y, 3. If I do 2y times 3 and double it, does it equal my middle term? Yes. So we take 2y minus 3 quantity squared. It's as easy as that. So second sign positive, perfect squares, yes. 2b, 7. 2b times 7 is 14 doubled, 28b. Yup. So we take 2b plus 7 quantity squared. That sign goes there. Look how easy. Now, this is 2 terms. So 2 terms. So is it the difference of squares? Is it the difference of squares? 2 terms, yes. Are both terms perfect squares? Yes. And then, is it subtraction between the 2? Yes. Okay. So what we do is we create conjugates. One's going to be plus, one's going to be minus. We take the square root as my first, square root as my last. That's equally as easy. 2 terms, subtraction, both perfect squares, yes, and subtraction. So you have y minus y plus, it doesn't matter if the negative comes first or the positive. I wrote the positive, it doesn't matter, those are interchangeable because of the commutative property. So 4k squared is a perfect square, 25 is a perfect square. We have subtraction, 2 terms. So 2k is my first, positive 5, negative 5. we have 3m, 3m, negative 8, positive 8. That's how fast we should be doing this. So we know this is not difference of squares. We know that we're going to check for binomial square. Binomial square has those 4 characteristics. 3 terms, second sign positive, first and third perfect squares. And does the middle equal 2 times the square root of the first times the square root of the last? 5x, 2y, multiply it and double it. Does it equal my middle? Yes, it does. So we get 5x plus 2y quantity squared. Yeah, man. Yeah. Difference 2 terms, subtraction, both perfect squares. Yes. So 9p minus 7q, 9p plus 7q. Remember, they have to be conjugates. They're identical, except the signs are different. 3 terms. Now, we didn't talk about this. We have to revert back to what we started with in this section was, is there a GCF? Can we do a common factor? Is there a common factor? Yeah. There's a common factor of 3. We can take out the 3 and we get that. And if you can't see that, then you have to do the prime factorization, find the GCF, look and see what the leftovers are. And now we look at this trinomial in the parentheses and we see 3 terms, second sign positive. Are the first and third perfect squares? And does the middle equal 2 times the square root of the first times the square root of the last? Yes. All of those are yes. So x plus 2 quantity squared. So that can be factored. We have a common factor of 5 and a c. Each of those has a c. So if we factor out a 5c from 5c cubed, we're left with c squared plus 6cd plus 9d squared. And is this, in the parentheses, a binomial square? 3 terms, second sign positive, perfect square for the first, perfect square for the third, square root. Does the middle equal 2 times the square root of the first times the square root of the last? Yes. And we get c plus 3d quantity squared. This is going to be easy for some of you. It's going to be challenging for others. If we take an r from both of these, this is the hard part. When you take an r from negative r, you're left with negative 1. And now we notice 2 terms. When we see 2 terms, subtraction, and both are perfect squares, we know that we're dealing with conjugates. T minus 1, t plus 1. That's always a good problem. Let's find a GCF. 4y. If we factor out a 4y, we're left with x squared minus 9. And x squared minus 9, our conjugates produces, that's the difference of 2 squares. Difference meaning subtraction of 2 perfect squares. X squared and 9 are perfect squares. Ooh, look at this one. That's good. That's a difference of squares. 2 terms, subtraction. Both of those terms are perfect squares, so they produce conjugates. 4n squared minus 1. Now let's do plus 1. No, let's do minus 1. 4n squared plus 1. Now, most students would stop here, but you have to check. This should be a warning sign. 2 terms, subtraction, and both are perfect squares. What does that mean? I can still factor this. This is that trick question that math teachers tend to give you. So we produce another set of conjugates from that. And then this is not, because it's not subtraction. It is 2 terms. First, and both terms are perfect squares, but it's not subtraction. So it would not be the difference of squares. Oh, perfect cubes. Hello. All right, this is the Algebra 2 part. Algebra 1 students, if you add this to your knowledge, you are going to have a huge advantage over your classmates knowing the template for this. So when we have, and we'll use the template, a cubed minus b cubed equals, it is going to be a minus b times the quantity a squared plus, what is it? It's going to be ab plus b squared. Had to think about it for a second. When we get a cubed plus b cubed, that's going to equal a plus b times the quantity a squared minus ab plus b squared, where we find the terms being cubed. So I'm going to show you a technique to factor this that will help. Oh yeah, no, they do it. This is good. So notice they break 8 into its cube. They rewrite it as a cubed value. They rewrite this as the cube value. So you know what to put into there. So when we're squaring stuff. So you'll see it when I do it. So this is easy. This is the sum of cubes. So we know that this is my a and this is my b. So my a value, my a is going to equal x, my b is going to equal 1. So when I see that it's the sum of cubes, it's a minus b, and it's a squared, I think it's plus. Is it the opposite of it? Yes. Plus ab plus b squared. So now we're going to plug in those a values. So x minus 1, and then this is going to be x squared plus a times b, which is x, plus b squared, which is 1, squared, which is 1. So that's how we would factor that. We're going to use that template. It's very, very helpful. Ooh, second problem, really? All right, this is how I do it. I would rewrite it. And then I would factor out a negative because we know that we can't have a first term negative. So I would write this as the difference of two cubes, and we would notice that this is going to be 4 cubed, and so my a is going to equal a, and my b is going to equal negative 4. Okay, or does it equal 4? I think it's just going to equal 4. I think we just do that. So if this is the difference, so we know that a minus b cubed, or a cubed minus b cubed, excuse me, a cubed minus b cubed is going to equal this template. A plus b, it's always the opposite, a squared minus ab plus b squared. So let's fill in our a's. A equals a plus 4. And then we get a squared minus a times b, which is 4a. And then let's do 4 squared, which is plus 16. Pretty sure that was it. Let's check the answer key, kids. Where is that answer key hiding? Let's see. This is section what? 4.5. Sorry. Please be patient with this interruption. This is number 23. Mr. Mack would just want to, oh yes, look at you, ugliness. So oh, and we forgot the negative on the outside. You would have that negative out there. Sorry. Yeah, so don't forget that negative. You have the negative. Oh, you get 4 minus a. I don't have that. Let's do this. Let's do this problem again. Clone page. Let's erase. We're learning, even the teacher. So if we write this, that is going to be 4 cubed minus a cubed. And that's going to fit in this a. What did I even write the? Oh, maybe I didn't even do that part right. A minus b and a squared plus ab plus b squared, where a and b, I know that's confusing. So 4 minus a And then 4 squared is 16. That's where I made my mistake. So my A is 4, 4A, and B, well, it doesn't matter, is A squared. And that's the answer they have. So I made a mistake. I don't know what I did there. And then you factored out that negative. But I think I just did, I think I used the wrong, yeah, I did the wrong. It's not plus, dummy. That's where I made my mistake. So that would be acceptable. That's the other answer. Sorry about that. My bad. It's okay. Can't be perfect every single time. Every single time. T cubed. We're writing these as cubes. That's 5 cubed. So we are in the cube, sum of cubes. So A plus B, right? Sum of cubes. And then we get A squared minus AB plus B squared. Well, my A is T plus 5. And then we get T squared minus 5T plus 25. Yeah, look how fast we just did that one. 24. Oh, yep. Yep, that's good. So I know I'm still working. I'll come up. I'm almost done. Oh, maybe not so much almost. I got like 10 problems left. All right. Perfect cubes, yes. That can be written as 10c, quantity cubed, minus 3 cubed. And then we have a minus b, a squared plus ab plus b squared, where my a is 10c minus my b value. And then we square it. That's 100c squared plus 30c plus 9. Woo! That is so good looking. That is 25. Just checking 10c minus 3, 100c plus 30c plus 9. Yeah, we're just plugging that base into that template. It's really the easiest way. All right, now I think we just got to find a GCF and then C. So they just continue to make it a little, woo! Sorry, we have a common factor. Do we notice that we have a common factor amongst us? It's both of those terms are multiplying the same thing. So we can factor that out, b plus 2. And if we factor it out, what are we left with? If we pull it out, we're left with a minus 3. And that's what is going to be left, a minus 3. So it's just like circling. If we do the prime factorization, we pull that out, and what are we left with? It's the same exact thing. Oh, this is tricky. So we're going to rewrite this as negative n plus 2 because these have to be the same. They have to be the same. And they are not. Must be the same. And they're not, so we rewrite it. And now let's factor out a negative from there. So if I take a negative out of there, that becomes positive, and we have n minus 2 because it's going to switch each of the signs. And now they're the same. So if I take out an n minus 2, I'm left with m plus 1. That's the tricky part. There's 2 tricky parts in this one. Second problem already. All right. GCF, no. This is 4 terms, so we're going to factor by grouping. So we're going to see, is there a GCF? Is there a GCF in these two? So we can take out a 5a squared, and that leaves us with 4a minus 1. And the second group, we're going to take out a 2, and that leaves us with 4a minus 1. And we see that we have like parentheses. So if we pull out that 4a minus 1, that leaves us with 5a squared plus 2. Factor by grouping. Factor by grouping. Typically when we see 4 terms, we think factor by grouping. Factor by grouping. So we can factor out a 10y squared. We're left with y plus 1. We can factor out a 3, which leaves us with y plus 1. We have y plus 1 in both of those terms. We factor that out. We're left with 10y squared plus 3. That's what you're shooting for, that type of efficiency and speed. Ooh. So I'm going to rearrange. I'm going to move these, and I'm going to move that over there. I'm going to write this as 9a squared b minus 9b minus 8a squared plus 8. And now I'm going to factor by grouping. I can factor out a 9b. That leaves me with a squared minus 1. I'm going to factor out, notice, first term negative of that grouping. So I'm going to factor out a negative 8, and I get a squared minus 1. Those are the same, a squared minus 1. They must. And then I'm left with 9b minus 8. I have to see, I can still factor. And they're going to be tricky. That is the difference of squares. So they produce conjugates. 9b minus 8. That's the tricky one. Yeah, I'm gonna move this with that one. So I'll write 5x squared y plus 5y minus 7x squared minus 7. And then I'm going to factor by grouping. I'm going to take out a 5y. That leaves me with x squared plus 1. I'm going to factor out a negative 7, which leaves me with an x squared plus 1. They have the same x squared plus 1. And take that out, we're left with 5y minus 7. This is not the difference of square, it's the addition of squares. All right, you got to be proficient at that. There are certain things that you got to be proficient in, and you got to be on top of your game. That would be, this section is a very important one to get out of algebra. You have to know all those things going into Algebra 2. I know it's being introduced in Algebra 2, but you needed to be proficient at it prior to coming into that class.